Activity 5, part 2. I forgot about electric motors, talking about electric motors. So, where we left off, I was talking about generators. Generators convert motion energy into electrical. Electric motors are the opposite, right? You put then electricity in and you get motion out. I mean, the possibilities are endless. Welcome to Is It an Electric Motor? This is a coffee bean grinder for Mr. Phillips' coffee. The Americanos, the espresso. You got the blades in there. Bzz. Got the plug. Okay. So we plug it in, get electrical energy in, and what do we get out? Motion! This is a paper shredder. There's just blades in there, man. Just blades in there, and you shove a piece of paper in there, and it shreds it! Let's shred something. Is this important? No, that's Mrs. Phillips' song. I can't believe Mr. Phillips is wasting paper during the coronid. Plug it in, electrical energy into the motion of the blades. Get it. Get it. Get it. Oh, it's on. Yes! Just kidding. It doesn't work like that. All right. Physics are so fun. My teacher, he just plays with electrical toys. Like a hairdryer. Plug it in. People are like, well, how is this an electric motor? It doesn't, it just puts out heat. People, there's a fan in the back there. Oops. There's a little fan in the back. How do you think the air gets blown out? You know, it gets sucked in through the back and then blown out the front. It gets blown through a coil, heated coil, basically a wire that's, well, whatever. All right, so electrical energy into motion. There we go. I just dried my scalp. Mr. Phillips's coronid mask. Is this an electric motor? I cannot donate this to any workers or anything like that. I've had this for a couple years. It is so nasty. Well, I mean, the filters need replaced, but it's so grimy. Oh, this is Mrs. Phillips was wearing this while sanding the other day. It's a little tight, a little snug. This thing's all goofed up. Yes. Yes. Oh, not plugged in, so we're not getting any electrical energy. I don't know if we could say we're getting motion out of it. Whatever, you don't use this to get motion out of it, really. No. Electric motor? No, I'm not showing the brand because I'm not sponsored yet. I don't have enough subscribers. People, if you get me to 10,000 subscribers, do we plug this in? We're not getting any electrical energy in. What do we get out of it? We kind of get motion out of it. I guess the motion of the cleaner. But you have to put motion energy into it. Okay, motion in. I'm not going to spray it because there's motion out. This is not an electric motor. Okay, it's just the little plastic bits in there that are pushing up against each other and forcing the other bits to move. So, Mr. Phillips' drill, hammer drill. His hammer drill. Pow. Do we plug it in? No, but it's battery powered. So electrical energy. Get motion out of it. Electric motors in here. Right? That's where the conversion of electrical to motion takes place. Mr. Phillips' cheap Harbor Freight. Harbor Freight owes me a sponsorship. Soldering wand. You plug it in, right? So you plug it in, you get electrical energy in, but you get motion out. Is that the point of this thing? Is that the purpose? No, it's heat. So motion or electrical in, heat out, that doesn't qualify as an electric motor. There are really no moving bits. All right, so anyway, electric motors then convert electrical into motion, the opposite of generators, which convert motion into electricity. Okay, part 2. Technically, really, people, all you need to do is if you have a coil of wire,
and you move the wire through a magnetic field, the magnetic force from the field generated by this permanent magnet, the magnetic force magnetically forces the electrons in the conductive path in the wire to move. Flow, current, electricity. Okay, it's just like there is current flowing through this wire. It has to be so tiny. I don't even have this like set up to measure anything, but I mean it's the nature. It's the way nature works. So, and again, like I was saying, it doesn't matter if you move the wire through the magnetic field or the magnetic field through the wire. Isn't it the same thing? It is. Can you even tell which one I'm moving and which one I'm holding still? Actually, I'm moving both, but anyway. See, it doesn't matter. This is a solenoid. It's really it's no different than coiling this up. It's this coiled wire that I have connected to the galvanometer so that current flows through it and this thing can measure it. The cardboard it doesn't do anything other than just like hold the wire in a solenoid shape. So it makes it easy to pass the magnetic field through. Again, it doesn't matter if the magnetic field is moving through the wire is moving through the magnetic field. You just need motion of one thing through the other and you get current, or at least it's measuring current. There's no battery in here, no power source. This isn't plugged in. So really, like, it's like, oh my gosh, there's no battery. There's no nothing. Yeah. So where does the energy come from? Where does the energy? The energy is not coming from some electrical source. Energy source is coming from motion. You get the conversion of motion into electricity. So really, actually, this little part here, motion into electricity through the solenoid, is what? A generator, right? And then we could carry this a little further by saying then that electricity gets converted into motion of the needle, of the galvanometer needle. That's an electric motor. So it's like, dude, it's like so like meta, man. It's just like, a motor and a generator and a motor and a generator. I'm not gonna have you guys memorize whether like, oh my gosh, like if the South Pole goes in, then it's positive. The South Pole comes out. If the North Pole, you don't have to memorize those specific. Oh, what I do want you to know or be familiar with is how things change. If I give you an arbitrary like default, if I say like, all right, North Pole going in results in positive current, like a positive reading, then you should know that, all right, well then North Pole out would be the opposite. That would be negative then. Or I could just make it something else. I could say, all right, North Pole going in gives us negative current. So then you'd be like, all right, well then North Pole going out gives us positive current. Just so that you know what causes the direction of current to flip. Likewise, what gives you more current. If I move the magnetic field through the wire or wire through the magnetic field more rapidly, more quickly, I'm going to get more current. And that's the law of conservation of energy, right? You put more energy in, you get more out. If you want more out, you got to put more in. Okay, that's proportional. Direction of current. Yeah, so if I place the North Pole through the solenoid and I get positive current, what is positive current? That's just a direction. And we don't even have to say like it's always clockwise or anything. It could be counterclockwise. It's just one particular direction. Let's just say North Pole going in is counterclockwise. North Pole coming out, that reverses the direction of current. So then that would be what clockwise? I forget what I even said. It's the opposite.